All right, so here we're going to start looking at modeling average costs. So these are going to be kind of more application problems. So when functions approach a horizontal line as x approaches some huge number, either positive or negative infinity, then that line is going to be a horizontal asymptote. Now the average cost function often approaches a non-vertical line as x approaches positive or negative infinity. So that's going to be called an oblique asymptote. So if a graph approaches a line that's neither horizontal nor vertical as x approaches infinity or negative infinity, then we get what, like I said, is called an oblique asymptote. So here we're given the cost function c of x is equal to that 1600 plus 0.25x squared, where x is the number of items produced. Now we're supposed to use the graphing strategy to analyze a graph of the average cost function. So we're not looking at the cost function, we're looking at the average cost function. Now state all the pertinent information and sketch the graph of the average cost function. Find the marginal cost function and graph it on the same set of coordinate axes. Include any oblique asymptotes, and then find the minimum average cost. All right, so what do we know about marginal cost? Well, that's going to be c prime of x. So this is going to be marginal, okay? Well, the derivative, that's going to be what? That's just going to be 0.5x. So that's going to be what our marginal cost is going to be. Now, what's our average cost? Well, c bar of x is going to be this whole thing divided by x. So if we split it apart, that's 1600 over x plus 0.25x, because we divide x and then one of them disappears. And so that would kind of be what our c bar of x is equal to. All right, so now let's go in and start doing our graphing strategy. Well, what do we know about the domain? Well, if we have costs, we can't have negative costs. So costs are always going to be 0 to some whatever unlimited value we have. Okay. So basically our x cannot equal 0, and so our vertical asymptote is going to be our x equals 0. Okay. All right. So what do we have next? We have vertical asymptote, we have that. So we can sit there and figure out an oblique asymptote. And oblique, remember, it said if we have some x approaching a positive or negative infinity, then we will get something. So if we plug in, this is going to like a huge, huge number. What's going to happen? Well, that's going to go to 0. Okay. And so if that goes to 0, really all we have is this 0.25x. And we're just kind of looking at the point where this one is going to 0. So we're just thinking about that at this point. And so what happens is we're going to oblique asymptote when y equals what? 0.25x. Okay. And we're only plugging it in here. We don't plug it in here because that's when that does that, that's going to be 0, and then it's going to be whatever that number is. That's what your cost is going to be, is 0.25 times that huge number. And so that's the only piece that comes into play. And so your oblique is just going to be based really on this here part. And so that's why we have that. All right, so for very large x, this goes to 0, and when that does, that's all that's left. All right, so I think that's all we can do for part 1. So part 2 now says, well, now let's find that first derivative. All right, so finding the first derivative, this is really 1600 x to the negative 1. So, and it's negative 1600. And if we put it back down there, it's x squared. Derivative of 0.25x is 0.25. All right. Now we have to figure out all the different partition numbers. So partition numbers, well, we know critical numbers also are going to be something. All right, so partition numbers, we have x equals 0. That's the easy one. Now, if we take and set this whole thing equal to 0, the 0.25 goes to the other side, and then we're going to multiply. So it's going to do something like this. We're going to have a negative 1600 over x squared equals a negative 0.25. Now we're going to multiply this by x25, or the 0.25 by x squared. Then we're going to divide by negative 0.25. And so we'll take that and divide it by a negative 0.25. And so then we'll get x squared equals, well, this is the same thing as multiplying that by a 4, and then negative times negative is positive. 4 times that's going to be 24. That's going to be 6,400. 64 square root of that's going to be 8, and the square root of 100 is going to be 10, so x is going to be equal to 80. And we can only have positives because we're only in a positive part of the domain. So 80 is going to be another partition number. Now, 0 cannot be a critical number because it doesn't work, but x equals 80 could be a critical number. Okay. So plugging those into here, we have 0, we have 80. This one in D, this one's 0. Let's say we do a 1 and we can do whatever, 100 or something like that. And again, this is for our derivative here. If we do a 1, that's going to give us a negative. So those are going to be negatives in that region. If we do 100, that's going to be make that 1600 divided by 100 squared. So that's going to be 0.16 negative, and then add 0.25. So that's going to be positives out here. So those are going to be positive. Okay. Now, that means if we're going down and then going back up, this is going to be a local minima. And so that's good because it says find the minimum average cost. So that will be our minimum average cost when we plug in 80. So that's a good thing. And so we have what? We have it's decreasing here and it's increasing here. All right. And so if we plug in our values, well, if we plug in 80, that's going to give us that's going to give us, so at minimum, our local minima is going to be 80 comma, it looks like 40. We have it's decreasing from 0 to 80, and it's increasing from 80 to infinity. And I think that's all we can get out of that piece. So now we have to go to the second derivative. All right, so now if we plug that back up here, that's x to the negative 2. So that's going to be a negative 2 times this. So 2 times that's going to give us 3,200. And then it's going to be a negative 3. So we're bringing that down. That's going to be x cubed. Okay. So here, our partition number is going to be at x equals 0 because we can't have 0 here. And so 0, we can't have that. And so any number we choose out here, basically anything we choose out here is always going to be positive no matter what we plug in because it's going to cube it and it's a positive number and it's a positive number on top. So everything's going to be positive. So it's going to be always concave up from 0 to infinity. Okay. All right. So now it looks like all we have to do is try to draw this graph. And again, this is not going to be good to scale or anything else like we've been doing all along. We just can't draw very well. And so let's call this out here because we know 80 and 40 is going to be 1 point. So 80, half of that maybe is there. So let's call that 40. And so this is going to be our minima. So let's maybe change colors again. All right, so this is what? This is our average. So we're finding C bar of X. This is what we're looking for. And what all do we have? Well, C prime of X, and this is going to be, so if we plug in X is 80, that's 40. So it looks like if we have to graph this on the same chart, we have to graph this. And so that's going to be something like that. And that's going to be C prime of X. That's our first derivative or the marginal cost. Now we also have to draw this piece. And so plugging all those in, we have a vertical asymptote at x equals 0. So if we do that, we could make that one red maybe and do something like that. Again, not perfect. Oops. What else do we know? We have our 80/40. So yeah, so I think now we just have to kind of think about what's going on. So now it's decreasing. That's kind of a minimum, and then it's going to be kind of going back up, to a certain point. And so the other piece we know was this oblique asymptote. So it's going to be kind of halfway between here. So that's going to be something like that. And so that's going to be our y equals 0.25x. That's their oblique. So that means when we start coming back up here, that's where it's going to be. It's going to be something like that. And then after that, it's going to be, something like that. So this actually is the minimum. It doesn't look like it in this drawing, but this is the minimum. It probably should come up a little different like that, higher, but that's okay. And so that's going to be our minimum value. And so on part B, it says, what's the minimum cost? Well, the minimum cost is going to be X equals 80 items because X is 80 in its items, and C bar of X is equal to what? 40. And I don't know if I want to assume $40 or $40 million or whatever it is, but it's 40, whatever it is. And we don't know if that's 80,000 items or what. It's just the number of items produced. So we don't have a lot of units here we can work with. And so we're just going to say it's 80 items and 40 here because we don't know what the cost is as far as units. It could be pounds for all we know. It could be something like that. All right, so I think that's all we can do in this one. Again, drawing is not the best of everything, but we're getting the ideal idea anyway as far as how things work. And so I think that's the key is being able to do the calculus to get something along the lines of what we have here and then get our values. So hopefully that helps you with this section.